WG64 is dying, but what for? The gigantic stars approaching farewell from the cosmic stages, for us, a spectacular research subject. After all, the stellar colossus is considered a hot candidate for the next supernova to be observed from Earth. But what dramatic changes indicate that the universe will soon be poorer by one of its largest known stars? How do the experts manage to create a breathtaking close-up of the celestial body, although it's about 160,000 light-years away from us? And above all, when exactly will WHG64 explode? The scale of a stellar giant. In our everyday perception, the Sun often embodies the ultimate in the cosmos. No wonder, since our central star has a staggering diameter of almost 1.4 million kilometers and alone contains 99.86% of the total mass of the solar system. Although our Earth would fit into the Sun 109 times in diameter and as much as 1.3 million times in volume, we must not forget that there are much larger giants out there. Stars that make even our mighty Sun look like a puny pinhead. One of them goes by the name WG64. Located around 160,000 light-years away from us in the Large Magellanic Cloud, this red hypergiant is estimated to have 16 to 22 solar masses and is around 1,700 times larger than our source of warmth and life. A star in its final throes. But that's not all. Observations have shown that the stellar colossus is already ejecting huge amounts of gas and dust from its bloated shell. At the same time, WG64 recently became the focus of the first-ever portrait of an extragalactic star. We now have another impressive close-up of a star thanks to a team led by Koichi Onaka from Andrés Bello University in Chile. More specifically, the researchers used the gravity instrument at the European Southern Observatory's Very Large Telescope in Chile to capture the magnified image of a dying star outside the Milky Way for the first time ever. The instrument used data in the near and mid-infrared range to create the image of a red hypergiant shrouded in a dense veil of dust, apparently in its final throes. Will WG64 become a supernova? What does this actually mean in concrete terms? Are experts expecting WHG64 to turn into a blazing supernova at any moment? Well, not quite. In an astronomical context, timescales are somewhat different. Although researchers do indeed assume that the star will explode in the near future, the word near still covers a period of 1,000 to 10,000 years in this case. For the universe, that's no more than the blink of an eye, but unfortunately, it's too long for us to witness this spectacle in the sky. What we can witness right now, however, is that WHG64 is undergoing a series of drastic changes that pose a few puzzles for scientists. The puzzling egg-shaped cocoon. From the close-up image, astronomers realize that the surrounding cocoon of dust and gas has a very different shape than expected. Specifically, it has a strangely egg-shaped form, and the experts do not yet know how this strikingly elongated shape came about. WHG64 has dramatically lost mass. One possible explanation is that the red hypergiant expelled the material of its hull unevenly, perhaps in the course of a particularly large outbreak. Alternatively, the asymmetrical shape could also be due to the influence of a companion star, even if this has yet to be discovered. A star in rapid transformation. Egg-shaped cocoons weren't the only surprising detail revealed by the close-up. Researchers also discovered that the star has undergone a significant change over the past 10 years. Specifically, the near-infrared radiation from WHG64 has increased significantly over the last 25 years or so, while remaining stable in the mid-infrared. According to scientists, this measurable change in the spectrum could be explained by the formation of hot dust in the immediate vicinity. In this respect, WHG64 is reminiscent of Betelgeuse, another gigantic star 800 times the diameter of the Sun, also nearing the end of its life. The final chapter of giants. A common feature of these departing giants is that the ejected stellar material first condenses into transparent grains of aluminum oxide and magnesium silicates. Subsequently, iron-rich silicates are deposited on these grains. These absorb more radiation, causing the near-infrared radiation generated by the heated dust to increase, while the celestial body itself appears darker in visible light. Co-author Jacco van Loon from Kiel University in the UK says, "The hypergiant WG64 is one of the most extreme of its kind, and any drastic change can bring it closer to an explosive end. And those drastic changes aren't limited to infrared variations. New measurements show that WG64 is shrinking dramatically. It has already lost 10 to 40% of its mass, and now has only half its original radius. Everything points to WG64 rapidly approaching its end, unless, of course, the companion star theory holds. In that case, the presence of a second star may have distorted measurements, meaning the supernova could be further off than currently expected." The short lives of giants. The lifespan of such large stars is generally less than 40 million years, making them something of a stellar mayfly in cosmic terms. Our Sun, by comparison, has already been around for 4.6 billion years, and will continue to burn like a normal star for another 6 billion years. Eventually, its hydrogen supply will be exhausted, and it will swell into a red giant before transforming into a white dwarf, surrounded briefly by a planetary nebula. Why stars explode? There is no question that supernovae are among the most spectacular spectacles the cosmos has to offer. But what actually causes stars to explode at the end of their lives? And what factors influence this brutal finale? Basically, the radiation pressure of a star becomes insufficient to counteract gravity due to decreasing nuclear fusion. The core collapses, triggering a powerful explosion. This shockwave is so extreme that it hurls hot gases into space. The radiation released makes the supernova shine brightly for about 100 days. Once the hydrogen-rich stellar envelope has been ejected, either a stellar black hole or a neutron star remains at the center. In the case of particularly massive stars, like WHG64, with more than 10 solar masses, experts speak of a Type 2P supernova. Although their progression follows the same pattern, each has individual traits, such as differences in luminosity or the shape of the remnant. Simulating stellar deaths. To better understand these differences, a research team led by Qian Yu from National Tsinghua University in Taiwan simulated over 1,000 variants of massive stars' development and supernova explosions. They compared the simulated light curves with the observed data from real stellar explosions. Their conclusion: the appearance of a supernova is directly linked to the properties of the star. They found, for example, that a star's metal content and rotational speed significantly affect the resulting supernova. Fast rotation, for instance, changes the inner structure of the star and increases convective mixing and mass loss, which in turn affects the brightness and duration of the explosion. Additionally, released energy and the amount of radioactive isotopes influence the outcome. A higher explosion energy results in a brighter but shorter supernova, while a higher isotope content leads to longer-lasting brightness. Why supernovae matter? Understanding the background of supernovae is important not just because they are dramatic celestial events, but also because the elements ejected in a supernova pave the way for the birth of new stars and planets, and thus the development of life. And did you know that your click can pave the way for a new subscription? Click the thumbs up and subscribe now to never miss a new video again. We'll see you soon.